Hi guys, my name is Jamin and today we're going to be doing a quick video on motion questions in mathematics HSC exams. Motion's a bit of a weird topic really because it's not applying any new content at all pretty much. It's just applications of differentiation and integration, two things we know how to do quite nicely. But what it's doing is it's applying it to a very specific scenario, the one-dimensional movement of a particle or an object along usually the x-axis. So to do these questions properly, you really need a strong understanding of the principles behind the mathematics. If you're just differentiating and integrating because you know how to do those things, but you don't understand why you're doing them, motion's going to be a tough topic for you because you really need to know why you're doing what you're doing. Because you need to understand how the position, where a particle is, the velocity, how fast it's moving, and the acceleration, how fast its velocity is changing, how these things combine to describe the motion of a particle or an object. Because questions are going to be testing understanding of these things in terms of scenarios. Will this particle ever return to the origin? Will this particle ever slow down or will it speed up forever? Etc, etc. You need to understand why you're doing the mathematics and where the mathematics is actually going to help you understand the scenarios. Motion questions can show up pretty much anywhere. It's pretty rare for them to show up in the last question of an exam unless you count last year. Last year was the first time they did it, and that's actually the question we're going to be looking at today. So just a quick revision of some of the things I've already talked about. So we usually define position along the x-axis. So normally we say, right, well, position is a function of t, and up what's over here could be anything, could be t squared plus 1, could be 1 on t plus 5, any function of t could appear on the right, but the position is just given by a time value. Then velocity is the rate of change of position, so it's the derivative of that function, and acceleration is the rate of change of velocity, which means it's the second derivative of that function. We move between these using differentiation and integration, just as you'd expect. There are a lot of different things that can be asked in motion questions, but again, I'm going to focus on one example from last year's HSC because A, it's the most recent, and B, it tests a lot of the common things. So let's get into it. So again, this appeared in the last question of last year's HSC exam, and we're given a velocity formula where said a particle moves in a straight line, its velocity after t seconds is given by this equation here. And then we're asked to do a few things. We're asked to find the initial velocity. We're asked to find the acceleration of the particle when it's stationary. We're asked to find, by considering the behavior of v for large t, to sketch a graph of the velocity. And then we're asked to find the exact distance traveled by the particle in the first 7 seconds. This adds up to a huge, actually, 8-mark question, probably the most that's been asked on motion for a long time. So this is a great example to look at to cover a few things at once and to show you sort of the upper scale of what they could be asking. So the first step is only worth a mark, so we expect it to be quite easy, and it's just finding the initial velocity. This is a mark that everyone should be able to get. This is a band 3 level question. So all we do, initial velocity means at the start, so when t is equal to 0. So pretty easy. We just go v is equal to 2 minus 4 on 0 plus 1, which is just 2 minus 4, which is negative 2 meters per second. You could also write meters per second that way. So what this means is that it's 2 meters per second to the left. Now notice that we're just saying to the left. This is because if we consider a number line, the negative numbers are out this way and the positive numbers are out this way. So if you have a negative velocity, that means you're moving to the left. Next, we're asked to find the acceleration of the particle when the particle is stationary. So this is going to require us to differentiate, because remember we have v. To get to a, that's the derivative of v. So the acceleration is given by the derivative of velocity. Now let's rewrite the velocity formula, just in the top right here, in index form. Just to make this next bit a little bit easier, save us using the quotient rule. And so let's now differentiate. The 2 is going to vanish. That's gone. Now what happens with the derivative is the -1 comes out the front, then we subtract 1 from that power, and multiply by the inside derivative, which in this case is just 1. So it's a fairly nice derivative actually. The -1 out the front with the -4 gives you 4. Then the bracket is still there with 1 subtracted from the power, and multiplying by 1 doesn't change anything. So, in fraction form again, that is our acceleration. And that's worth half of the 2 marks. So, we're asked to find the acceleration of the particle when the particle is stationary. So, the first step is to figure out, okay, when is the particle stationary? Stationary means that velocity is equal to 0. And this is a big part of the motion topic, taking the buzzwords and saying, okay, what does that mean mathematically in terms of the quantities that I have? If an object is stationary, that means it's not moving, so v is equal to 0. So that's what we do. We say v equals to 0, and we solve this equation. This requires that 4 on t plus 1 is equal to 2. We get 2t plus 2 is equal to 4. And that simplifies quite nicely to t equals 1. So that is the time value we're looking at. So all we do now is say, well, when t is equal to 1 second, then a is equal to 4 on 1 plus 1 squared, which is 4 on 4, which is 1 meter per second per second. So the acceleration of this thing, when it's stationary, is 1 meter per second, and because it's positive, it's to the right. For the third part, we're starting to get a little bit more interpretive. By considering the behavior of v for large t, sketch a graph of v against t for t greater than 0, and we have to show intercepts. So let's first do the first part of the question by considering the behavior of v for large t. What this means is that as t gets really, really big, so after 1,000,000 seconds, 1,000,000,000 seconds, 1,000,000,000,000 seconds, what value does the velocity approach? Now, you can do this mathematically, or you can do it intuitively. It's up to you. I'm personally going to approach it mathematically. So what we're mathematically doing is taking the limit as t approaches infinity of v, which is 2 minus 4 on t plus 1. Now, when you take the limit as t approaches infinity, what you're going to notice happens is that this denominator here gets really, really, really big. It's 4 on a billion, a trillion, a quintillion, right? 4 on such a huge number is essentially just going to reduce to 0. So this term vanishes. So what you actually get is just 2, because as time gets really, really big, that fraction is going to disappear. So what that means is that as t approaches infinity, our velocity is going to approach 2. And it's going to approach it from below, because it approaches from below because it starts at a lower value. It starts at -2, and it's going to increase from there and approach 2 ever so slowly. Let's now get into the graph. So we draw our axes, time on the horizontal, velocity on the vertical. And let's put in the information we know. We know that the initial velocity is -2. So we'll put that intercept down there. And we know that it's approaching a value of 2. On a graph, this represents an asymptote. So I'm going to dot in a line here. That's v equals 2. Now we're also asked to find intercepts. Now, remember in the last question, we wanted to find when the particle was stationary. That's when v equals 0. That is going to give us the intercept that we want. That happens when t equals 1. So I'm going to put an intercept here and call that 1. And that's pretty much all we need to do the question. You could put in another guiding point when t equals 3, v is equal to 1. So you could pop a point over here as a guide if you wanted to. Besides that, you've pretty much got the shape there. It just has to come up and approach v equals 2 asymptotically. You might want a little bit more of a curve on that based on how narrow or wide your graph is, but something like that is what you're looking for. The key elements are this asymptotic behavior for v equals 2, this intercept at t equals 1, and this intercept at v equals -2. If you have those 3 key points, you're going to get the full 2 marks. Right, so this last question is actually more difficult than it seems, and there's 2 main ways to do it. I'm going to show you both. So the first, well, what we have to understand is that the exact distance traveled by the particle, we can't just take the final position and subtract the initial position. The reason for that is a little more obvious when you look at the graph. The particle isn't always moving in the same direction, it's turning around. So if we look at the graph, the velocity starts at a negative value, then it goes to a positive value. So essentially what it's doing is it's going backwards, and then it's going forwards, right? So it's sort of looping back on itself a little bit. This makes it tricky. We can't just do a straight subtraction. We have to be more clever. There's 2 ways to do it, pretty similar in what they're actually doing mathematically, but perhaps you might find one more conceptually easy than the other. The first way to do it is that you can always consider distance traveled as area under the velocity curve. So I've just drawn the velocity curve there. That's the 7-second mark. You can always consider distance as an area underneath the velocity curve, provided you account for negative areas, and we've got one in this question. So you could find the distance traveled by saying, okay, remember this intercept is at 1, right? So you could say, right, I'm going to take the absolute value of the area under my velocity curve from 0 to 1. Then on top of that, I'm also going to add, don't need an absolute value this time, the area under the next part of the curve from 1 to 7. That will give you the distance traveled. So the key bit will be to integrate velocity. Remember that this will just be 2t when we integrate, and this is going to turn into a logarithm. This is a logarithmic integral. So it's going to turn into -4 natural log of t plus 1. So that is sort of our integrand. That's what we get when we integrate. So we go 2t minus 4 log t plus 1 from 0 to 1, absolute value. And the next one will be the same. It just won't have the absolute values in it. But what's inside the brackets will be the same with different limits. And let's go ahead and substitute. So in this first one, we have the absolute value. Substituting 1, you get 2 minus 4 log 2. Then substituting 0, we actually get nothing. So it's just the absolute value of that plus, and over here, we'll get 14 minus 4 log 8 minus 2 minus 4 log 2. So let's simplify this up. Simplify this just a little bit. So when we do this, the absolute value here, 2 minus 4 log 2, if you pop that into your calculator, that's actually a negative number. The absolute value will turn it into a positive number, and it does that just by swapping those 2 numbers around. The rest, let's just expand it, taking into account any sign changes at the end with the brackets. Let's group like terms. We have, let's cross off as we go as well. We have 8 log 2 in total, minus 4 log 8. And then for the constants, we have 14 minus 4, so it's just plus 10. Now it looks like we're done, but we can actually simplify this a little bit further. Using our log laws, we remember that 4 log 8 is 4 log 2 cubed. And where the log law comes in is that we can bring this 3 out the front here. Because remember, the log law is that the log of x to the y is equal to y log x. Powers can be brought out the front of logarithms. So what this means is that this actually becomes 12 log 2. And that means we can tidy this up a little bit more. We get 10 minus 4 log 2 meters. That's the distance traveled in the first 7 seconds. So that's one method. There is another method. Let me show it to you. So this next method, if you don't spot or don't feel comfortable with this area under curve idea, is probably for you, but it's probably a little bit more algebraically difficult. But I'll let you be the judge. So what we're going to do this time is, instead of definitely integrating to find areas, we're just going to indefinitely integrate to get back to x. So when we do this, we get the same as before. We get 2t minus 4 log t plus 1. But of course, since we haven't used limits of integration, we've done an indefinite integral, we now have a constant. Now, there's actually no way to evaluate this constant in this question. A lot of the time there is. In this question, we're not given any sort of information about the particle's position, so we can't evaluate that constant. However, that doesn't mean that we can't use it and watch it cancel out as we try to find a distance traveled. You'll see what I mean. Now that we have a position formula, we now can use the idea of subtracting positions at different times to get distance traveled. We just have to be careful. Remember, what we figured out was that the particle starts somewhere at t equals 0, goes to the left for 1 second, and then for the rest of the time goes to the right, so for another 6 seconds. So there's sort of 2 or 3 key points we need to know. We need to know where it is when t equals 0, where it is when t equals 1, and where it is when t equals 7. If we know these points and subtract them carefully, we can get the same answer as we got before. So let me call this first distance here d1. We get that distance by taking the time where it is at t equals 0 and subtracting where it is at t equals 1. So when we do that, x0 is just substituting 0 into that, you get c. And substituting 1 into that, you get 2 minus 4 log 2 plus c. So watch what happens. Therefore, distance 1, the difference between these two things, the c goes away. We're subtracting the constant, it cancels. And so you just get this expression here without the constant. You get 2 minus 4 log 2. Now, however, just like before, this is a negative quantity. Distances, we need to be adding positive things. So to be completely correct, let's pop an absolute value around all of these. And in an exam, you can notice these things as you go. You know, you don't have to have pre-planned absolutely every detail. If you notice you get a negative answer somewhere and you think, oh, got to apply an absolute value, do that. And we get the same thing that we had in the first part of the previous expression. Now, a similar thing is going to happen if we try and find d2, the distance traveled from 1 to 7. When we do that, we already have x1. It's 2 minus 4 log 2 plus c. And x7 is 14 minus 4 log 8 plus c. And I'll use the same trick of simplification that I used in the last slide. So it'll just turn into 12 log 2 plus c. And when we subtract those to get d2, the same thing happens as happened on the left. The constants are going to go away. So even though we never knew what that constant was, it doesn't matter. We can still use this method. And so what we get, if we're careful with signs, is 12 minus 8 log 2. The total distance traveled is the sum of d1 and d2, or the absolute value of d1 and d2. And so what that gives us is 10 minus 4 log 2, which is exactly what we had in the previous version of the working. So you can see both work. What this does is it sort of takes what the definite integral does and does it separately. It makes it a little bit easier to understand what the definite integral is actually doing. It takes a similar amount of time. This method might be a tiny bit longer, but whichever one you find conceptually easier to understand is the method you should employ. The other thing to keep in mind is that a lot of the time, this constant, you will know it. But in this case, we didn't, and it didn't matter. It doesn't always matter if you have an unknown. A lot of the time, it will cancel. So I have two different methods there. Both are great. Whichever one you think works best for you is what you should use. As a few last minute tips for motion, remember to include units. So if you're giving an answer and it's a time value, include seconds or days or whatever the unit may be. If you're giving a distance, give meters or kilometers or whatever the unit may be. It's unlikely that they will take marks off you for this, but they very well could, and you don't want to take any chances. And beyond that, including units is a good way to keep yourself on track and make sure you're finding a time value when you find a time value, etc., etc. Very easy to get off track in motion, so it's good to always have these little checkpoints. One sort of question we didn't cover in this video is justifying a statement. So we sort of did it when we did the limit of velocity as t approaches infinity. The important thing is to always use mathematics. This style of response, the particle doesn't return to the origin because it never turns around after moving on from the start. See that a lot? It's awful. Markers hate seeing that because it's just a wish-washy statement. If you give this answer, it looks like you have no idea what you're talking about. If you use mathematics, so give specific statements of what values are what at given times, use limit notation as we did in the example today, all this sort of stuff, it's going to add to the sophistication of the response, which isn't normally important in mathematics, but when you're justifying or explaining what you're doing, it's quite important. So make sure you're doing that. That'll do it for this video. If you have any questions about motion, it's a really tricky one, I know. Feel free to jump onto the 2-unit math forums on ATAR Notes. I'm always hanging around. There's a lot of people there ready to answer any questions you have about motion or any other part of your study for the mathematics exam. Thanks for watching, and I'll see you guys soon.